Good afternoon. So from today we'll start the second part of the lecture series, that is characterization techniques for advanced materials. So being Madam is on urgent leave, so I will start taking lectures from today. She may join in between, or she may start her course after end of my part. So I'm Dr. Keshi Barik from BRC. So I'll take mainly that the characterization techniques for advanced materials. So when you think about advanced materials, so that is a material which has engineered properties, and that has to be created through the development of specialized process and synthesis methodology. So you have to choose a specialized process as well as methodology which will ended up with a raw material that has properties which you want to get it, like the engineered properties. So these advanced materials, so main thing is you need to tune the properties of the materials. So that properties of the material mainly depend on two factors. One is structure, and another is morphology. So in both of these two, morphology and structure has to be characterized thoroughly. So for that, you need better characterization technique to achieve proper materials. So properties and performance of the materials are strongly dependent on the structure and morphology. For that, we need different characterization technique. For example, said for structure, you can do two ways. That is one, some of the techniques that are based on diffraction, and there are some other techniques which will be based on the scattering. So both the diffraction and scattering, so that the scattering diffraction techniques like X-ray diffraction, electron diffraction, and neutron diffraction. In scattering also we'll see X-ray scattering and neutron scattering. Similarly for morphology or interface properties, that you can use either interface techniques or imaging techniques like XPS, X-ray absorption spectroscopy, secondary ion mass spectroscopy, scanning electron microscopy, SEM imaging technique, transmission electron microscope, or AFM STM. So most of these characterization techniques I will cover, except that AFM and STM, I'll just give a little bit glimpse, but all other techniques I will discuss more elaborately. So that all these techniques, if you see that whether it's a diffraction technique, whether scattering or imaging techniques, all these techniques depends on the interaction of radiation, that is photon, electron, or neutron with the matter. So you have an object, with that object, that matter, how this radiation interacts. So in today's lecture, so before going into the different characterization techniques, first we will see the basics of interaction of radiation, that is photon, electron, and neutron with matter. So before going to the interaction of radiation, if you see the interaction of light, so how it affects the matters. So mainly that light interacts mainly three ways. That is, one is absorption, then scattering, and third is transmission. So in the absorption process, that light interacts with the matter and it completely absorbed by depositing its energy. And in case of scattering, that it interacts and it can be scattered or deflected back from the original direction, or and deposit part of its energy to the matter. And in case of transmission, it interacts and is transmitted through the material without unaffected the materials. So if you see this diagram on the right side, you see the absorption process on the top and scattering process on the bottom. You can see the incoming beam, which is a photon, that's h nu, it interacts with the matter, and then you can see you have a fluorescence phenomena can be occurred. You can create photoelectron, you can create a secondary electron like Auger electron can be generated. Similarly, with scattering, that scattering may be an elastic scattering as well as inelastic scatterings. And the remaining, that whatever the light, that unattenuated attenuated ongoing beam will transmit it. So transmission is mainly the attenuated beam that is going out of the matters. So if you see the attenuation, that is the of an incident light beam, can be considered a combination of two phenomena, that is scattering and absorption. So you have attenuation, it's mainly scattering plus absorption. So if you have a material that is 100% light intensity is coming onto the material, and that has 90% attenuation, then 90% that 10% is absorbed, and remaining 19% is attenuated from here. And in subsequent step, it follows the similar path. Every step, it's 90% will be transmitted through this beam, and at the end you will get, if I0 is the incident beam and I is the transmitted, that attenuated beam, and then you will get that I equal to I0 into e to the power minus mu x. That mu is nothing but fractional linear attenuation coefficient per unit. Coefficient unit is per centimeter. So all of you know this equation, that how this light interact with the matter. You can express it that mu is mu by rho, by m by mu by rho is a mass absorption coefficient. So we can express that how that light is attenuated by this process. So after, similarly, that radiation also interact with the matter. So the interaction of photon, electron, and neutron as they transverse matter are stochastic, and they obey the law of chance. Like if there is a material, then only it will interact, otherwise it will go as such. So, and it's very with different behavior. Like with different material, its interaction is different. So if you see the photon in general have few interaction and are exponentially attenuated. So that photons interactions are expressed in terms of cross section. So that how the cross sectional area that it interacts, so that is expressed, the photon interaction is expressed in that terms. Individual interaction and attenuation coefficient for the passage through the bulk media. So photon will interact with the material, and whatever that interaction terms that will express in terms of cross section. Similarly, electron express large number of interaction as compared to photons and neutrons. In general, after interaction, that the electron lose energy until they stops. So they'll keep on interacting till they're completely absorbed or is completely stopped. That means this is expressed in terms of electron range. How far electron we can move, that will express by a term called electron range that we'll discuss later, and then that material stopping power. So that is the how that material can be absorbed, can absorb that electron. So depending on that stopping power, the interaction phenomena of the electron mainly depends. But in case of neutron, the interaction is very low, because whether small size as compared to the nucleus in relation to the atom, the nucleus is very small as compared to the atom. If you see, that's why neutrons have very low probability of interaction among these. So the electron express large number of interaction, whereas neutron has very short, very few interactions. We see here that the neutron or X-ray, that is photon or electron, so they can interact with the atom as a whole, or it can interact only with the nucleus itself. So you can see here the electron, the X-rays, the electromagnetic interaction, and it can be scattered. X-ray scattering both can be occur. And similarly, that tightly bound inner electron shells are there, and loosely bound outer valency shells or extranuclear space are there. So that four type of interaction, it's mainly gives that one is atom whole it can interact, or it can be outer cell electrons or inner cell electrons, or that surrounding space that can interact. You can see that electron also will give electronic interaction, electron scattering, whereas in case of neutron, you will see neutron scattering, and then there will be dipolar interaction, that is being neutron has a magnetic moment. So because of the magnetic moment, you have a magnetic scattering which is possible from the neutron. So this neutron interaction, X-ray or electron interaction is the basis of all characterization techniques. So first we'll discuss about the interaction of X-rays, that is photon with metal, how it interact. So when you see that that incident X-rays is fall on a specimen, so there are various emission effects or various signals can be generated. First of all, X-rays can be absorbed inside the specimen, so that will generate lots of heat. So specimen will get heated. So The first process will occur is the absorption process. The second is that it can generate a fluorescent X-ray or scattered X-ray. So what is the incoming X-ray photons that will interact with the specimen? So it can either, scatter its path, and changes its path by scattering phenomena, or it can generate a fluorescent X-rays. So this scattering can be two types. One will be incoherent scattering, another is coherent scattering. So coherent may be from the bound charges, but incoherent are Compton, or loosely bound charges from where that incoherent, X-rays will produce. Similarly, it can also generate that X-ray can be absorbed, and you can generate, electrons can be produced. That electrons will be photoelectrons or Compton electrons, recoil electrons you will get. Or you can, that incident X-rays can be generated transmitted beam. So if you see, the most of the X-ray scattering and X-ray diffraction technique will depends on that how the scattering or fluorescent X-rays is producing, and that electron will mainly that will take place in that how electron microscope or XPS photoelectron spectroscopy we generate from this, from transmitted beam, that some other techniques are also related. So in addition to this, the X-rays can also refracted or reflected at a very small angle. Like the angle of incident is very, very low, so there is a probability that you can get, X-ray can be refracted or reflected. So first coming into that, this scattering X-rays, how this coherent incoherent scattering are produced. That coherent scattering means that's elastic scattering. So that means that energy is conserved. That before interaction and after interaction, the energy will be conserved in this case. That means when an energy of incoming X-ray photon is substantially less than the binding energy. Like every electron has a binding energy, and that's why that electron is surrounded around the nucleus. It is a specific binding energy. So if your incoming X-ray has less the energy less than the binding energy of the electron, then the radiation undergo changes in direction without changing wavelength. That means that whatever the X-ray, incident X-ray, that will not generate, no electron will be ejected out here, and there will be no energy transfer, and no ionization process will occur here. So that's why this interaction occurs mainly with very low energy of X-ray of 15 to 30 kilo electron volt. You can see if incident photon is lambda I, that wavelength is lambda I, and scattered photon will be lambda f, that is final, that scattered photon lambda f. So you can see the lambda I is equal to lambda f. So there will be, it will be, that elastic process, there will be no loss of energy in this case. So coherent scattering that you will see here, that mainly contribute to the background. It doesn't give any peak or any information. It is just to contribute the background, that is thermal. Diffuse scattering or scattering due to defect. The material has some defects inside. With that defect, that X-rays interacts, or scattering due to slits, pinholes, binders, or air scattering. So these type of scattering are mostly correlated to the coherent scattering. But if you see incoherent scattering, that where the energy is, the changes will occur. So that will be, one is Compton scattering. That is an example that occurs when incident X-ray photon is deflected from the original path by an interaction with an electron. So that X-ray is going through the material. It is found a loosely bound electron is there. You can see the incident photon H nu, that's lambda I. It found as a loosely bound electron. So what will happen? It interacts with the electron. Then electron will deviate its path, and similarly that incident photon will scatter in another direction. So that electron is ejected from its orbital position, and X-ray photon lose some of its energy due to interaction. Because during this interaction, that the photon, that wavelength mu will changes to mu dash, that because it lost some energy, but it continues to travel through the matter along the altered path. That electron will be move on, travel through the matter. So energy changes depends on the angle of scattering here. Not that how the scattering that occurring on the system in the matter, so that will decide the energy changes, not the matter here. And scattering X-ray photon has less energy than it has less energy, and that it has longer wavelength and less penetrating. Since it has a less energy, we have a scattering, that X-ray has, penetrating depth is quite low as compared to the incident one. And if you see that the Compton scattering, the collision kinetics is based upon the conservation of both energy and momentum here. So you can see that that kinetic energy, that h nu, that energy equal to h nu minus h nu dash you will get here. So you have a del lambda, a change in wavelength will occur. So that you can find out during this equation. So incoherent means that it doesn't contribute to the diffraction. So darkness of the background of the diffraction, we will see the diffraction pattern. So there is a dark background that you will see. So those type of, inelastic scattering, that Compton scattering will contribute to that type of backgrounds. So it has no phase relation among the incident and the scatter wavelength. So it's directly proportional to the electron density. If your electron, the system has high Z value, high electron density, your interaction will be, strong in that case. And as I told that most of the X-ray interaction is expressed in terms of cross section or electrons, so that sigma is proportional to Z, that is the electron density. So another phenomena that occur during X-ray, like Compton scattering or elastic scattering, another factor is called photoelectric effect. So photoelectric effect means that we have a action that when an incident photon eject, that electrons are moving around the nucleus, you can see the X-rays is falling one of the electrons. Once that electron goes out, so that incident photon eject an electron, and the process is called photoelectric effect. And this is called photon-electron interaction. That X-ray is the photon, and you have an electron surrounding the nucleus. That once that X-ray photon falls on the electron, that electron moves out. You can see here photoelectron is moving out, and you create a vacancy. And that vacancy exists due to the removal of the electron, and thus one or more characteristic X-ray will be produced, and the vacancy will be filled by the higher orbital electrons. Like this is unstable state, and then the high energy state, that here electron will fall on this vacancy state, and then some X-ray will be produced here. And that other relaxation other than that photoelectron, that other relaxation process of an excited atoms are sometimes, instead of photoelectron effect, you can see also fluorescence, that is emission of photons, or emission of electron, that Auger electron process will occur. So that Auger electron that we will discuss later. So mostly the photoelectron effect is mainly due to the removal of electron from the core level, and then the higher energy level electron will fall that empty space, and it will remove. It generates some that characteristic X-ray will be produced because of this photoelectric process. And then this photoelectric effect here, that photoelectric effect can only takes place if the photon energy is higher than the binding energy. That is, to overcome the binding energy of the electron towards the nucleus. So once it overcome the binding energy, then only that that X-ray photon will be able to eject the photoelectron. So therefore, the energy of the photoelectron is equal to energy of the incident photon minus energy of binding energy. So that here the photoelectron photoelectric effect is mainly predominant for low energy photons, but that has higher binding energy than the electrons. So mostly the low energy photon used to gives that photoelectric effect, and higher atomic number material jet with atomic number that has high, so those are mostly give photoelectric effect. And probability of interaction is mainly proportional to that Z to the power 4 by E to the power 3 in the proportional to this terminology. So in addition to photoelectric effect, there are other factors is coming into picture, that is a pair production. So that when X-ray photons, when high energy X-ray photon passes near the atomic nucleus, when nucleus here and there are atomic electrons are moving here, then what happened? You have a cool nuclear has a Coulombic field surrounding that nucleus. So the nuclear Coulombic field, so that X-ray photon will interact with the nuclear Coulombic field by a process called pair production. And during this process, the photon, X-ray photon will become converted into two particles. One will be electron that is negatively charged, another will be positron that is positively charged. So to create two particles in that this for electron and positron, it requires minimum of 1.02 MeV mega electron volt minimum energy is required to create this particle. So that excess energy of photon is given to the particle as kinetic energy, which allows them to travel. It will travel a little bit on the due to creation of from the point of creation. So these two electron and positron, they will move little bit, and when that excess energy will be given to the photon. So these can undergo charged particle interaction and losing energy during the each interaction. So the prior production occurs in the field of nucleus. The interaction cross section varies. Each z square is proportional nuclear charge, that z is proportional to z square. So this will occur, that pair production only occurs when a high energy, that more than energy is 1.02 MeV, that interact with the atomic nucleus. So because of that interaction, you will get these two factors. So if you see the photon interaction, mainly the three phenomena that I discussed, one is Compton effect, another is photoelectric effect, and pair production. You see here that mostly for low energy photon, photoelectric process is predominant. So energy is in the range of 10 to the power -3 to -1. In that range, low energy, the photoelectric effect is predominant. But in the middle range, that is all range, that is mainly Compton, will be mid-range, it will be prominent, whereas at high energy pair production mainly occur energy above 1.02 MeV. So we see this is the nature of the curve. You can see here that the interaction of photon with water molecule at low energy is photoelectric effect, and how Compton and pair production varies. But this pattern will remain same in most of the material. But you see for that each case the interaction dominance will be same, but that there may be shifting of the the curve shifting may be occur, but the effect at low energy is photoelectric, then Compton, then pair production. It will be follow similar pattern in all matters except there is shifting in the position of these curve positions. So in addition to these three phenomena, the fourth phenomena is occur when a photon interacts with the matter is called photodisintegration. That's direct interaction of energetic photons, that is very, very high energy photons that directly interact, and it absorbs the nuclei. So it gets absorbed, and then after being, once that the photon get absorbed, then that it goes to the excited, by the way, after being excited by the photon, so the atom, that system will be goes to excited state, and the nucleus emits a proton, or more likely neutrons you can emit. Like a gamma ray will generate, or a proton or gamma and neutron will be generated. So this type of photodisintegration mainly occur when you have a threshold energy of 8 mega electron volt in all nuclei except the deuterium and beryllium, that occurs. The deuterium occurs at 2.22 MeV, whereas beryllium at 1.67 MeV. So, but all other nuclei you will find that this minimum threshold energy 8 mega electron volt is required for photodisintegration to occur. So far we discussed that how photon interacts with the matter. So mainly three ways, that is pair production, and then photoelectric effect, then Compton scattering. And in addition, there is a high energy case, you will see how the photodisintegration occurs. So now we'll discuss about interaction of electrons with the matter, how electron interact with the matter. So if you see that electron is an elementary particle having a negatively charged, that rest mass is 9.1 to 10 to the power 31 kg for a charge, which, as you know, that minus 1.6 into 10 to the power minus 19 coulomb. So this is a negatively charged particle. So it behaves, excited electron behaves as a both particle and wave characteristic that by de Broglie equation, and that we have as a both particle as a wave. You can see wave of electron beam can be coherent like X-rays. It can be coherent or incoherent. If you see here, if a coherent waves, you can see the same wavelengths. So how they are, one above the other, that heights, that all these things. So if we say incoherent waves of different wavelength, so there will be because of incoherent, there will be destructive interference may be occur. In case of coherent, you can get a constructive interference As you can see, if you see that incident, you have a matter here, you have a matter, and this matter, if you see here, the electron beam falls here, and then different interaction you can see here, that same electron can be bounced back here. So that will be a backscatter electron. After interacting with the matter, that electron will bounce back, that is backscatter electron, or it can generate that electron can be absorbed inside this matter, and it can generate a secondary electron. So that will be a second electron will come, or it can produce an X-ray. So if you see that backscatter electron and second electron, these two will be used in scanning electron microscope. And then that you can create an Auger electron, a third electron can be come out from here. So that Auger electron will give about Auger electron spectroscopy. And then if that electron beam you will transmit it through this, the direct beam, that will give you, transmission electron microscope. So whole electron microscope is generated to is associated with this interaction of matter, whether it is backscattered or secondary, going to allow it is attached to the SEM, scanning electron microscope. X-ray is attached to the X-ray, the EDAX analysis, energy dispersive spectroscopy, EDAX analysis in case of SEM or TM, or if you have a direct beam, the transmitted beam, so that we will use as that transmission electron microscope. If you see the interaction of electron with matter, so that as I told, there will be elastic collision. In that case, no energy will be transferred in that case when you have elastic interaction. So here that no energy is transferred from electron to the sample. As a result, electron leaving the sample still has original energy. With the same energy, you can see here this interaction after interaction going this way with having same energy, both E. So electron penetrating into the electron cloud of an atom is attracted by the positive potential. So you have a Coulombing potential in case of nucleus, that electron cloud there that will attract towards the positive potential. Here, when elastic interaction deflects the electron beam along new trajectory, this is the initial trajectory in this direction, now it moves to another trajectory without causing them spread laterally. So the closer the electron, if you see, you can see the incident electron here, so it's going here in this way, so it's scattering is less. So similarly, it goes to the close to the nucleus, your its scattering is very, very high. So you angle that scattering angle, the closer the electron comes to the nucleus, the higher is the scattering angle. You can see the scattering angle is much higher in this case. So in that case, you will get a backscatter electron that is strong elastic scattered very near the nucleus, may result in a beam of electron having specimen that is the backscatter electron. So that will be used in case of scanning electron microscope. So here the probability of electric scattering increases how with Z square, the square of the atomic number. Heavier is the atom, more stronger is the in the interaction you will see, and it decreases as electron energy increases as 1 by E square. But in case of inelastic collision, the energy is transferred from the incident electron to the sample. You can see here that here you have a electron, it can interact the matter, then it has energy E minus W. That W energy is transmitted, goes to the it lost that much energy. So energy is transmitted from incident electron to the sample. Thus, after the interaction, energy is reduced. The W energy is absorbed by the system here. So this energy loss happens gradually with the distance is travel inside the atoms. So how these electrons moves inside the atoms, the energy loss will be accordingly, it will be progress. So it is dominant energy loss mechanism, mainly the inelastic scattering, the main sources of energy losses, that in this case, and the interaction produce, because of this interaction, inelastic interaction, that atom can be excited, or can ionization of the atom will occur here. So if you see the inelastic collision can produce different system things, like you can see here, it can create that incident beams comes fall on the inner core, and that electron that moves, it replaces another electron, so you can able to get a secondary electron can be generated, or you can create a photon, that X-ray can be emitted here because of this incident electron. So that X-ray will be used in elemental analysis, or or you can generate Auger electrons. That can be used for Auger electron spectroscopy. So higher energy electron of incident beam removes an electron from the inner cell. That high energy, that electron fall on this and the inner cell remove, and that hole will be created, by filled by the electron from the upward state. You have an electron here, so that electron will migrate here. Then you can able to get an X-ray also. So that X-ray or Auger electron process will occur. So in addition to this, that how this secondary electron or backscatter electron or the Auger electron or X-ray fluorescence, you can also see some background radiation in case of electron interaction. So that background radiation is called Bremsstrahlung emissions. So that electron emits that Bremsstrahlung due to the acceleration caused by electrostatic field of atoms. Like in the atom, we have electrostatic field. So once that electron moves inside the atom, so it will interact with the matter and slowly it will lose some of its energy. So that is mainly that background radiation emission you will see because of the electron interaction. In each Bremsstrahlung event, the electron with energy E generate a photon of energy W. So that means that during each Bremsstrahlung interaction, some photons will generated, and that will give some background radiation. So in addition to that, you can also see that positron annihilation, that an electron, that sometimes the positron penetrating to a medium can annihilate with the electron. Like as I discussed that in case of pair production, that X-ray photon, divided into two particles, that is one positron and electron. Similarly, positron interact with the electron, you will get a two photon. You can get here two photons. So it occurs when kinetic energy of the positron is very, very large, and then the absorption energy is much higher. Then what will happen? You will get a E positive and E minus here. So these are the mainly way of how this, electron interact with the matter and produce different types of scattering, that secondary electron or backscatter electron or other phenomena. So here, in case of both inelastic and elastic scattering, so that electron will interact up to a certain volume. So that is called interaction volume. You can see here the electron beam coming here, then it can move like this in the whole that area or that volume where the electron will move. So that is called that in the three-dimensional region, that movement of the electron, that will be expressed in terms of interaction volume. So that depends on that how the electron energy and also the material properties. If you see the region generated because of this phenomena is called interaction volume, and the range of this, how the electron will move, the total range like this or this range, that is called electron range. That interaction volume can be simply described by a single parameter called electron range. So electron range is thus a simple value that is useful for rough comparison of the comparison and scaling of various signal distribution. Like for material to material, that interaction volume varies, as well as how it depends upon the energy of the electron. The size and shape of the interaction volume, that depends upon the both that electron beam of the elastic and elastic scattering. And you can see here the interaction volume, how it depends on the electron energy, atomic number, that's material property, and Z value and density of the material. You can see here, if a low energy material, you can see the interaction volume at low Z material, low Z material, you can see low atom, you can see how its penetration is high. But if high Z material, low kV, its penetration is less. So the interaction volume here is this type. But in case of high kV, you can see the penetration here, low Z material, its penetration is much higher, whereas here high Z, high kV, the interaction volume is symmetrically increases. So it's all depend on that how the interaction volume of the incident electron beam. You can see the blue line, and then in the gray the system, and you can see that yellow line is mainly at how the trajectory of that electron is moving, and this trajectory, that electron range, is mainly depend on this equation, that e to the power 1.67. So specimen is here, it's assumed as a flat specimen, and thickness enough to be the electron of work. So electron will not transmit it. So electron will keep on moving inside that system, and you will be able to get this type of interactions. So you will see here that the interaction volume here, you can see the electron beam falling on this surface, mainly on the top surface you will see that secondary electron will be generated here, and then Auger electron in this case will be generated on the top layer, that within 1 nanometer length scale you will be able to see that only Auger electron and secondary electron will be generated. And if you see, up to 100 nanometer, you will see that secondary electron generated on the top surface 1 nanometer. There you will be able to get Auger electron spectroscopy, or X-ray, X-ray fluorescence spectroscopy, or you can able to see that backscatter electron in the next volume, that is up to 500 micron, or if you go continuous deeper and deeper, you will able to get different types of X-rays and as well as cathodoluminescence. So that is the mostly that interaction volume that decides the which type of electron is coming out, whether it's X-ray, whether it's secondary electron, or whether it's backscatter. If you see the backscatter electron, so the coefficient of backscatter electron depend upon that number of backscatter electron is coming by the number of electron that is bombarded, injected into the specimen NB, NBS by NB, that will depend on intensity of the electron. So the backscatter intensity increases as the Z number, that the atomic number is higher, your backscatter will be more. So it also depends on the theta value. You can see here the incident is 90 degree, that is that is much higher here, maximum at the normal things that backscatter, but that is really not possible. So at a slight tilting angle phi, you will able to get that backscatter, and it, depending upon the tilt angle, the angular distribution of BSE, backscattered electron, is defined here. So similarly, if you see the secondary electron, in case of second electron, that loses that a loosely bound outer shell electron, like you have a different shell here, whatever the outer shell, these are the lower shell, the outer shell electron that loosely bound. So this out, once you in that electron falls, the outer electron will come out, and that will give the secondary electrons it will receive. The second electron coefficient is number of secondary electron produced divided by again that number of that electron being interact in the system. So sometimes what happens, the second electron generated while the incident being passed through the specimen is designated as SC1, because that SC1 can also generate sometimes that backscatter electron also. During this process of secondary electron generation, what is the first electron generate, second electron generate, that sometimes creates a say secondary another backscatter electron, that is called SC2. Low resolution secondary electron is also generated, and here the emission of secondary electron is very sensitive to the condition of the surface, because of low kinetic energy severely limits the range of secondary electron. So if you see here that secondary electrons is mainly generated in this area here, so that in that area, so it is mainly depends on the that one is tilt energy. The tilt energy increases. So if your tilt similar to this, if your tilt energy will increase like this, your secondary electron generation will decrease. So maximum you will get at low tilt angle, like similar to backscatter electrons. So that if you see that the electron interact with the material and it can produce secondary or the backscatter electrons or transmitted electrons, so that will be useful for different characterization techniques. So when we will discuss individual characterization techniques, we will more elaborately will discuss different types of electrons, and then now coming to the interaction of the neutron with the matter, how the neutron will interact with the matter. So as you know, the neutron is a mass, is a 2000 times of electrons. It's a higher mass, and it has a magnetic moment, that is a nuclear magnetic moment, and it's a indirectly ionizing radiation. You can see here that neutron was discovered by Chadwick, who got Nobel Prize in 1935, and see how barium and helium interact, and you can get carbon with a one neutron will comes out, and that neutron changes the whole development, Newton diffraction techniques and Newton scattering. So those things are nuclear reactor come into picture here. So if you see the properties of neutron, so neutron properties are mainly neutron is elastically neutral, and they can go deeper into the matter since they don't have any charge, so they can go deep inside, and it has a magnetic properties. It since microscopically magnetic, so this shows a magnetism. and its wavelength is very, very low, and the angstrom wavelength can show structures and the energy of million electron volt can show its motion. So here both structure and dynamic both can be studied. By using low wavelength neutron, you can analyze the structure as well as million electron volt energy. You can see the motion of that neutron. You can see dynamic characteristics. So if you see the types of neutron, there are mainly three types of neutron. Thermal neutron, that's also called slow neutron, energy less than 0.5 electron volt. And then you have an intermediate energy neutron that is in between 0.5 to 10 kilo electron volt, or fast neutron, which has energy is much higher. And this neutron also follows de Broglie equations. You can see the energy of a neutron will be inversely proportional to lambda square here. So you can see it has both particle as well as wave characters like electron. You will see neutron has both particle and wave characters. And this neutron can be generated in three different sources. Mainly one is spontaneous fission reaction that you can see in a research reactor, that is there is a chain reaction occur. You can see fission process here. Uranium-235 undergoing fission and produce krypton-92 and beryllium-147. You can generate 3 neutrons here. Minimum that in this type of fission reaction can produce neutrons. And in a research reactor, you have a chain reaction, so that 1 neutron for fission is progress and other neutron usually observed. And then in addition to that, there is photonuclear interaction is there, or neutron generator there. Neutron generators are available nowadays. You can see here, this is a spallation process, that's internuclear interaction. You can see here, where first coming photon when falling in an atom here, lead, you can see it goes to the excited state, and then you can able to get, neutrons can be produced here. Similarly, with high energy laser driven process, you can able to also get, neutrons can be produced here. If you see that in spallation, you will get much more number of neutrons, or laser driven 30 neutrons, whereas in a fission process, you get 2 to 2.5 or maximum 3 neutrons. If you see the neutron, the brightness or the flux, that how the intensity of the neutron beam in comparison to X-ray beam, you can see here, neutron's brightness is much less, 10 to the power 15, and whereas X-rays, that is rotating anodes X-ray 10 to the power 16, or when synchrotron X-rays are undulator, or when regular 10 to the power 26 or 10 to the power 33. And similarly, flux is much high in case of X-ray, and in neutron is very less, 10 to the power 11. Because of less brightness and less flux, when you go for a real sample analysis, you need to do much longer time is required for neutron analysis than for X-ray analysis. X-ray analysis can be done much faster. If you see the interaction of neutron with a matter, that bound neutron in a nuclei are much stable, and free neutrons are unstable, and the lifetime is very less, that is 14.76. Meaning if a free neutron, that is unstable, and knows that interaction of neutron, that no charge, so that it can interact with the nucleus. So being that no charge, it will easily interact with it can penetrate and it can interact with the nucleus. The nuclear forces leading to this interaction is very short. You can see that neutron, that nuclear radius is 10 to the power minus 13 centimeter. So neutron have passed close to the nucleus to be able to interact. So, and because of small size of the nucleus in relation to the atom, neutrons have very low probability of interaction. Like comparison to electron and X-ray, neutron interaction is very less because of that smaller size, and it interacts with electron by electromagnetic moment. So both magnetic interaction is possible in case of this. So you have an elastic interaction and a neutron interaction, inelastic interaction, and dash or absorption, but neutron can be captured inside the material, or you can cause fission. So there are different types. So you see here, neutron has high penetration depth, and it can be scattered by the nuclei, not the electron. So being it's a neutral, it passes through the electron cloud and interact with the neutron, it will scatter from the nuclei. So they leaves a portion of their energy until they thermalized or absorbed. Still their absorption process occur, so neutron will keep on losing its energy. So neutron is quite sensitive to light elements, light atoms like hydrogen, oxygen, this type of, you can easily find out the characteristic of this surfactant or polymers, right? Those are composed mainly hydrogen, oxygen. By neutron scattering or neutron diffraction techniques, where X-ray can't be used. You can see different phenomena here, that the X-ray scattering, the neutrons are produced, or you can production of charged particle, deuterium or helium, how they are produced, or it can go to fission process. So neutron has the ability to cause various types of interaction. If you see that how the slow neutron interacts, the slow neutron can be captured by the nucleus of the observing material. But since it is slow moving electron, it can easily absorb inside that. You can see an example, sodium-23 can take one electron, it will give you sodium-24, and then a gamma ray can be produced. So this type of compound is unstable, and this compounds will emit gamma rays or charged particle. There will be n gamma, n electron, n alpha, or n proton you can able to get here. When the compound nuclei emits only gamma ray, this is a sodium that emits only gamma ray, we call it a radiative capture. And the probability of this capture is inversely proportional to the energy of the neutron. It's mainly how it's lower the energy, more is the observing here. So in case of that neutron. And if you see the neutron capture, different radiative capture, one is neutron with hydrogen, it can capture and gamma produce, or in case of cadmium, so it can be observed and you can able to get the radiative source. In case of lithium, you can see that boron can observe that one neutron goes to lithium, charged particle emission here, helium is charged particle emission, or it can be proton charged particle emission here in case of nitrogen. So these are the most of these common things that used in neutron dosimetry, or in hydrogen that is used in the component of human tissue. So human hydrogen also that can produce some radiation dose and use in dosimetry or shielding this type of neutron reaction. So slow neutron is captured more easily inside the body. But if you see this slow neutron, and that it can also go through a fission process, so that neutron interact with uranum 235, so 2 to 3 neutrons are available in each in fission reaction, and then the absorption of the neutron produce a compound nucleus. You will get a compound nucleus, and that compound nucleus is gain the kinetic energy of the neutron and the binding energy of the kinetic energy of the binding energy of the neutron, both it gain, and that it will got a once that energy exceeds the critical energy, so you have the fission, so it will break into 2 parts, so you will be able to get 2 to 3 neutron in each reaction. And then if a elastic scattering, you see the first neutron, so first neutron mostly goes elastic scattering, so that neutron that interact with the particle approximately same mass. So that means of a photon. So both are same. A neutron, they interact with the substance which is a element which is almost similar mass, that is same photons. So like a billiard ball striking to each other. So it's a billiard ball type of big balls that interact with each other. So material rich with hydrogen, like water, wax, concrete. So there are a lot of hydrogen. So neutron of the equivalent mass, so they will interact with this kind of interaction. So similarly, the energy of the recoiling nucleus is absorbed by the medium. The incoming electron will absorb, and this nucleus will start recoiling. And so total energy here is conserved. So recoiling nuclei quickly become an ion pair and lose energy through the excitation and ionization through the process of biological material. And this is the most important mechanism by which neutron produce damage to the tissue. So neutron will absorb inside this biological material, and then it will create biological damage to the system through the process of excitation and ionization. And similarly, if the first neutron also interact with like inelastic scattering, if energy is much higher, is more than 10 mega electron volt. So here the neutron interact with the particle is much higher Z, like iron or the bigger Z value. The neutron interact with those type of heavier element, that's analogy to the ping pong ball striking to the bowling ball. So if a small ball striking the big ball, so that type of interaction is here. So here energy transmitted to the target nucleus, and then neutron is re-emitted with lesser energy. So you can see incoming neutron here interact the nucleus, is gamma energy is produced, and emitted neutron which comes out. So energy transmitted to the target nucleus, and then neutron re-emitted. So nucleus left in excited state. So because of this interaction, the excited state and relax by emitting neutrons, gamma rays, or charged particles. So here also total energy is conserved, and inelastic scattering occurs primarily with high Z material, and it doesn't have a tissue dependent. High Z material goes through the fast neutron with interact with high Z material inelastically, whereas low case it's elastically. So if you see here neutron interaction, so neutrons are born very fast and they slow down during the process of interaction. You can see if the energy of 1 mega electron volt will interact the nucleus, it loses energy, and step by step it keep on losing energy. Still the energy is less than like about 0.025 electron volt, and finally to get capture inside the nucleus. So first neutron convert to thermal neutron, and then it will capture inside this. So here the nuclear interaction is mainly depends on the neutron cross sections. That probability of the interaction, how that interaction will occur, that will depends on the cross section. It's expressed in terms of bar, that is nuclear interaction is the number of scattered neutron per second by number of incident neutron flux. That is 1 barn equal to 10 to the minus 24 centimeters square. So it depends on the nuclide and the neutron energy both. So total cross section is the sum of separate cross sections for all processes. Like you have a neutron that is in that interaction volume, total interaction volume, neutron, how scattering volume, capture, as well as fission. So sum of these will be total. So mesoscopic section, if you see microscopic section, the total cross section of all atoms is summation of n number of atoms, so sigma total. So to increase the interaction probability, you need a moderator that neutron has to slow down, and then it will has to thermal velocity, so you'll be able to get this type of neutron better interactions. So the interaction, if you see here, like electron that I equal to I0 e to the power minus mu x is characterized by also characterized by the attenuation length, mainly that equivalent to the electron. So you can, so neutron lose energy when they interact with the material. So beam intensity drops continuously as it propagates to the material. You can see that it expresses this mu is equal to 1 by lambda. And then the scattering length is expressed, each interaction that is expressed in a scattering length, that Bj, that is a neutron, depends on the how the isotope, and the depends on the Q value that we will discuss. For some isotope, it can be negative. That like in X-ray, that is always positive, that you have electron dependence on electron density. Here, that scattering length is electron density independent of the electron density. It's sometimes a positive and sometimes it's a negative. So it's a randomly vary. That scattering length randomly varies from different atoms. So that we will discuss later. So the macroscopic cross section is used for neutron in place of linear or mass absorption coefficient here. That is used for photon attenuation. In case of photon attenuation, we use mass absorption. Here, the macroscopic cross section that is used in case of neutron interaction. So, so far what I have discussed is mainly the different types of interaction of photons, electrons, and neutrons. How does it interact with the materials? So, and based on these different techniques are, characterization techniques are there. So, we will discuss first how this the X-rays are interaction with the material that we discuss. Now we'll discuss X-ray and its properties. In after a 2 to 3 minutes break, we'll discuss that how this X-rays are produced by this, and how its properties and how it interact with the metals. Okay. So we'll meet after 3 minutes. So now we'll discuss about X-ray and its properties. So after discussing the interaction of X-ray, neutron, and electron, so how these X-rays are produced and how how its properties are varied, that we will see here. So if you see that the X-ray properties, that mainly X-ray was history. If you see, X-ray was discovered in 1895 by German physicist named William Röntgen, and while studying cathode rays. So while studying cathode rays, so he saw a stream of, a guy, some new type of, the energy are producing, that he termed as a X-rays. And that time X-ray means stands for unknown. So when Röntgen observed a new type of radiation that is possibly due to the interaction of the electron with the glass wall of the tube, that could be detected outside the tube. So that this new type of radiation is observed first time, and this could penetrate an opaque substance and blacken. What he found that X-ray can be penetrate through an opaque substance and blacken a photographic film or produce a fluorescence or ionization gas. So being at that time he was unknown about that what is it, so he termed as X-ray. So X-rays are also defined as the weightless package of pure energy with no electrical charges, that doesn't have a charge and travel in wave along a straight line with specific frequency and speed. That means it's an electromagnetic radiation, and that has the weightless, and it has no electrical charges and travel in the wave manner along a straight line. So that's why it says a particular called a photon. So if you see the properties of X-rays, that it has a physical properties, it is also some chemical properties or some biological and physicochemical characteristics. You can see here a broad electromagnetic spectrum. So X-ray is a shorter wavelength, mainly 10 to the power minus 9 to 10 to the power minus 11. And some meter in that range, X-ray is a very shorter wavelength, and it is high energy. And if you see the physical properties of X-rays, so X-rays are mainly belongs to a family of electromagnetic radiations. So wavelength between 10 angstrom to 0.01 angstrom. So very low wavelength, and it travel at a speed of light in the vacuum. So it's very high speed, and it is possible, it's invisible to eyes. Our naked eye, we can't see those X-rays, and they can't be refracted or deflected by magnetic or electrical field, as they don't possess any charge, since they're uncharged particles. So like neutron, they have magnetic properties, so that can be reflected by a magnetic field. So here, being neutral, so it can't be reflected or deflected from the direction. So they are pure energy with no mass and transfer energy in the form of quanta. That's why it's called as photons. So they can penetrate various objects, and degree of penetration mainly depends on the quality of the X-ray beam and its intensity and wavelength. Is based on this wavelength, how intense is the X-ray, and how is the quality of the beam. You can say penetration depth is varies with the materials. And then you can see that X-ray can induce color changes in several materials. You might see if a methylene blue will exposed to the X-ray, it will completely bleached out. The apple green color of sodium, platinocyanide, is turned dark green, and then light brown, and finally dark brown. It's the color change as some of these chemical changes occurs. And similarly, X-rays destroy the fermenting power of the enzymes. So the fermentation power of the enzymes will be lost. These are the chemical losses. And the X-ray affects the photographic papers or films in the same way as is visible light. So on the photographic paper, so it affects that. The X-rays excites biological materials also, which enables them to take part in chemical processes. Otherwise, they are normal. Like some of the biological material, so they don't undergo any chemical changes because of the X-ray excitation. It can goes to the chemical changes, so that also generate biological damage. They are transmitted through the healthy body tissue, but absorbed by the bone. That you can see that that is useful for the X-ray in medical diagnosis. That's X-ray film that we get by the a medical X-ray done. It's mainly because the body tissue are transparent to X-ray, so easily pass through bones that is absorbed, that high-jet material it absorbed inside the bones. So we were able to get a proper image. If you see the production of X-rays, so X-rays are produced mainly by conversion of kinetic energy of electrons into electromagnetic radiations. That means you have a shell tube. Inside the shell tube, you have here you have a anode and you have a cathode. Here you can see here you have apply high voltage here. Because of the high voltage, so that electrons will be generated, and that electrons will fall on the tungsten target here. So that the product striking here and produce high energy, like that X-rays will be produced. Mainly these are produced by striking of high energy electron beam on a target material. You can see here that for the X-ray generation, you mainly need three types of things. One is electron source, that high energy electron will be produced by applying high voltage. If you provide high voltage by thermalic emission, the electrons will be generated here. Then electron acceleration potential, you need a potential gradient here. So you can generate a high potential, the electron acceleration potential. Then a target material, that is tungsten here, conjugated to copper anode, that's tungsten, that X-ray will be produced. So the major component, that is the cathode, that is the electron source, anode, that is acceleration potential to generate a high potential, acceleration potential, and you have a targeting device here, that is in there, or a envelope, that is whole sealed vacuum envelope to to contain that X-ray inside this. So composed of a filament, that cathode is a filament, and then anode is a target electrode, and it's maintained a high positive potential difference with respect to the cathode. So because of this potential difference, the electron will be migrated here and it will interact with the target and produce X-rays. So if you see, electron released from the cathode are accelerated towards the anodes by an electrical potential difference and attain its kinetic energy. So once it attains its high that kinetic energy, then only it will produce that X-rays. So when they fall on the high energy on the anode, the energy loss of electron takes place by scattering an excitation process and produce X-rays along with heat. The intensity of the electron beam decides the intensity of X-rays. If you are high energy in X-ray with bright intense, then you're able to generate high intense X-rays. So about 99% kinetic energy is converted to heat during this process. Only 0.5 to 1% of electron energy is capable to produce X-rays. So mostly all energy is give rise to heat generation here. So if you see, because of the heat generation, so how that you will see how this heat is produced in this process, that you can see the positive electron that is coming from the cathode, this electron will interact with the outer shell electron of the target atom. We have a tungsten, that is a target atom, and the outer shell electron is there. So it will interact with the outer shell electron, but don't transfer energy of ionization of outer shell electron. So if it emits the outer shell electron, because of the ionization process occur, that electron, that is one thing, but if you don't transfer enough energy for ionization the outer shell electron, then what will happen? The outer shell electron simply raised to an excited state. If sufficient electron, that energy is not transferred to the this system, to the target, what will happen? The outer shell electron will not ionize. So what will happen? That will simply raise to the excited state or higher energy level cell. So the outer shell electron, after some time, immediately drop to the normal energy level and emissions of infrared. So that infrared radiation is mainly gives rise to the heat. The constant excitation and return of this process, you can see here, this electron comes here, it excites here, then it comes back and again interact another atom, it's come back. So this process, it's a continuous process, excitation and return. Because of this lot of heat will be produced. So mainly that will produce loss of heat here. Only 0.5 to 1% of the electron energy is capable to give rise to produce X-rays. So during this X-ray production, what happens? So X-rays are produced by two things. Like one is Bronsted, that is background radiation, another is characteristic radiation mechanism. So the projectile electron here, that coming here, the projectile electron, it interact with the inner shell, the target atom. So then what will happen once it interacts, that each electron in the target atom has a binding energy. So it's bound with the nucleus with a particular energy that is called binding energy of that element and of that cell. So once your projectile electron has kinetic energy is much higher than that binding energy, so then what will happen? The projectile electron with high energy, if the high enough energy, can totally remove this electron from the electron cell. So this electron will come out. So unfilled cell is here the once then we create a vacant site. So a hole will be created. So then this is highly unstable. Then outer cell electron will fall into this. So this electron will fall here, or this electron will fall here. Then the X-rays will produce. So this X-rays production is from depending upon the energy level from where K cell, L cell, M cell. So they are named that we will discuss. So if we have only that electron is capable to remove that electron, then only characteristic X-rays will be produced by jumping of the electron from the higher state to the vacant sites. But if that is only just energy not sufficient, only ionization, and then the coming down state is occur, you will be able to get only radiation will be that is called that mostly background radiation that mainly gives rise to heat production. So, but if you have energy enough, you will be able to get X-rays. So, a characteristic X-ray is produced with an energy equal to the difference between the energy of the electron cell, binding energy of the electron cells. That means what are the characteristic X-ray? That electron will depend upon the kinetic binding energy and the kinetic energy of the systems. So, if you have a sufficient kinetic energy, it will overcome the binding energy so that X-ray will be produced, and that X-ray has a energy equal to the difference between the binding energy of the electron cells. Like this binding energy and this binding, the inner cell and this outer cell, if you see here, it is K and L. So binding energy of K cell and L cell, that a difference will be produced as a characteristic X-ray here. You can see here that how the characteristic X-ray is produced. If a K series and a L series, M series, N or O, you can see here, once a K electron moves out, that vacancy will be there. And the excess energy, that vacant site will be filled by another electron from L cell. That from L cell, it come an electron here, that will fill this K cell series. So that will be called K alpha. And this excess during this process, that the L cell electron falls to fill the vacant orbital of the K cell, so you'll able to that excess energy of that L cell, that electron will be released as a characteristic X-ray during this transition. So energy released is equal to the difference between the binding energy of the each state. Here, if it from the L cell, you will be able to get K alpha. It is M cell, it will be K beta. Of its N cell, it is K gamma. Similarly, L alpha, L beta, or L gamma are produced depending upon the which energy level the electron is filling to the vacant sites. And similarly, if you can see inside also K, that L cell is, you can see that divided into L1, L2, L3, that is 2S, 2P, 1 by 2, and 2P, 3 by 2. You can see if it is that is K alpha 1, K alpha 2, or the different type of different. Similarly, that L alpha 1, L alpha 2, or different transition will be depending on the M cell or N cell. So M cell has a 5. Instead, you can see 3S to 3D5. So depending upon these different types of alpha 1, alpha 2, beta 1, beta 2, different types of transitions, characteristic X-rays are also emitted. So during this, you can see that binding energy are unique to the given element. If you have a K cell, that's tungsten. If you see here, and molybdenum and rhodium, you can see K cell of a tungsten has a binding energy of 69.5 and whereas molybdenum is 20.0, rhodium is 23.3. So that means that binding energy are unique to a given element, and the emitted X-rays have a discrete energy that are characteristic to that element. So depending upon the which X-ray is produced, can able to do the chemical analysis, whether it's coming from K cell, whether it's coming from L cell, and that energy, since it is unique to that particular element, you can identify the element based on that X-rays. So target material used in X-ray tubes are generally high-jet material like tungsten or molybdenum or rhodium, where Z is much higher. In case of tungsten, 74. So high-jet materials are used as a X-ray source. That here in the target material, and you get binding energy directly proportional to Z square. So because of this, the high-jet material used, as the energy of the incident electron increases, above the threshold energy of the characteristic X-rays produced, percentage of characteristic X-ray also increases. That means it's all depends on that potential, that whether you are 5% 80 kVp versus 10% 100 kVp, that potential that volt kilovolt you are applying. So depending upon that, the X-ray production can be varied. So if you see here during the X-ray production, you can see here that K cell, L cell, you can see here these are the characteristic X-ray lines, K alpha 1, K alpha 2, K alpha 2, K alpha 1, K beta. K beta has higher energy than that of K alpha or K alpha. You can see here K alpha in case of tungsten, how this K alpha the energy is varies. So a variety of energy transition occurs from the adjacent alpha or non-adjacent beta cells of the atom, giving rise to discrete energy, like you can able to K alpha 1, K alpha 2, or K beta will generate. So within each cell, other than K cell, there are discrete energy subcells are there that I described in case of L cell, that 2s, 2p, 1/2, 2p, 3/2. So that many subcells are there. So depending upon them, the characteristic fine X-ray splitting will occur, whether K alpha 1 or K alpha 2. The characteristic X-rays other than those generated by K scale transition are unimportant. So mostly K cell transition are used widely, a little bit L cell. So beyond that, we are not used for element analysis purpose. So if you see, so during that, you can see here, you have a K alpha 1, K alpha 2, and K beta. You can see the proportional ratio of K alpha 1, K alpha 2, K beta is K alpha is 6:3:1. So you have a high intense K alpha 1, and then K alpha 2, then K beta. K beta is a higher energy than the higher wavelength, likely 1.16, 1.6, it is around 1.5, that K alpha 1 in that range. So if you see that when you have you can see when a target material is a molybdenum, you have a K alpha 0.71 angstrom. When you have a copper, it's 1.54 angstrom. In chromium, it is 2.24 angstrom. You can see here in case of molybdenum is quite low. And here you can see you have a K beta that sometimes interfere in X-ray diffraction pattern. So what we used to do, that K beta has to separate it. It has to filter by using specific, filter material. So if you have see here that in case of molybdenum, the filter is zirconium. In case of copper, filter is nickel, which is just filter is chosen as a Z-1. That is because so it's just absorption coefficient of nickel is equal to that of K beta energy. So it's immediately absorb that one. So you'll get K alpha only. So K alpha 1 and K alpha 2 will be present in that case. Sometimes using K alpha 1 and K alpha 2 can be also separated. So in case of X-ray, so when you are producing characteristic X-ray, there is probability of generation some fluorescence. Because if you see, the chromium is the target element that can be generate lots of fluorescence like titania, scandium, and calcium. Those elements, if you use analysis of this type of element in chromium target, you will be able to see a strong, background. Similarly, you can see if most of the iron case or copper, if you go for iron Fe3O4 or any iron-based analysis or cobalt crystal structure analysis, you will see a lot of background that is mainly because of X-ray fluorescence, because these are the material, the target material, and these are the fluorescence with this element only it may analyze it will produce fluorescence. That some atoms, that means some atoms absorb the incident X-rays and fluoresce them as X-ray in different wavelength. That this material, like if you go for cobalt with copper target, cobalt will absorb some of the X-ray incident of the incident, and it automatically generates some fluorescence. The absorption of X-ray decreases with a diffracted signal, so that that fluorescence X-rays increase the background noise. If there is a lot of fluorescence occur, then what will happen? You will get lots of noisy background in case of X-ray diffraction pattern. To increase the background noise from fluorescent X-rays can be removed by using a diffracted beam monochromator. If a monochromator or energy sensitive detector, like energy wise, you can differentiate and able to remove this noise. Similarly, using this type of monochromator, you can also differentiate K alpha 1 and K alpha 2. You can be used that separated diffracted using different this type of monochromator. In addition to the characteristic X-ray, there is a background radiation also occurs during X-ray generation. So that is called Bremsstrahlung radiation, is mainly produced when the projector electron interact with the nucleus of the target atom. So you have a that electrons. So you have a target neutron. So that incident that the X-rays that for the electron interact with the nucleus of the target. And then during this X-ray generation, that electron which you are bombarding onto the target, so that electron interact with the target atoms and it's produce a background radiation. When the projector electron completely avoid the orbital electron and passed by the target nucleus, it slows down and changes its course, leaving kinetic. You can see here incident ray 1, 2, and 3. When you have a incident ray 1, you can see that maximum impact with the nucleus. When you have a 2, is a less, and 3, you have very, very less. And in this case, you can see when interaction 1, that is impact with maximum energy, and in case of 2, it is distinct interaction, low energy, and close interaction with moderate energy in case of 3. And because of this, electron interaction with this internuclear side, so what will happen that it will lose kinetic energy, reappears and as an X-ray and called as a Bremsstrahlung. So the loss of during this process, the electron loses kinetic energy, that reappears as an X-ray, that is called slow down radiation. So distance between the projector electron and the targeting nucleus determine the kinetic energy loss. How the energy loss, how close to the nucleus that incident electron beam, that depends on that energy loss. And direct impact on the electron with target nucleus result loss of all its kinetic energy and produced highest energy X-ray. That means that incident beam 1, it directly enters the nucleus, which produce highest energy. And you can see the Bremsstrahlung will give you a background radiation here, broad background radiation, and in that you can see here in that broad background radiation, you will K alpha 1, K alpha 2, or K beta. So this broad relative output is mainly due to the Bremsstrahlung radiation. You can see here the X-rays of low energy with much greater abundance. With low energy X-rays is mainly associated with the Bremsstrahlung, and X-rays have a range of energy. You can see a range of energy from 10 to 90 kilo electron volt. This background radiation. An average X-ray is mostly this 1/3. You see 10 to 90, so around 30 to 40, 1/3 to 1/2 in that is the highest X-ray energy here. So X-ray production coefficient, that's intensity, will be influenced by the target atomic number Z and kinetic energy. How that Z of the material is high, and at the same time, what is the intensity of that incident electron beam, that is the kinetic energy of the incident beam. These two parameters affects the X-ray, how the characteristic X-ray is produced. So if you see, the X-rays are used in different purposes. So you use for security purpose, that in case of airport or cargo analysis, these X-rays are used for baggage analysis. And in case of medical process, in the radiography, we generated that X-ray films which helps in analyzing that fractured bones and all these things. But if you go the analytical method, the security and medical purpose, that we will not discuss. So we will mainly discuss that how these X-rays are used in analytical characterization techniques. So in that we will discuss mainly how the X-ray related to X-ray diffraction spectroscopy, diffraction analysis, X-ray fluorescence spectroscopy, X-ray photoelectron spectroscopy, and how XRF is related to which wavelength dispersive spectroscopy, energy dispersive spectroscopy for element analysis, which XRF used mainly for element analysis. For X-ray photoelectron spectroscopy will be used for oxidation state or chemical characteristics, or X-ray diffraction for phase analysis or crystal structure analysis, and those type of properties that we will study in next classes. So in the next class, we will mainly discuss X-ray diffraction techniques. So in today's lecture, if you summarize what we have studied, so that mainly that how that material that radiation interact with the material in three different ways. The three methods, that is X-rays, photons, the X-ray photons, neutrons, and electrons. So the wavelength of them are almost same, but the energy, if you see, the energy of X-rays is 10 to the 4 electron volt, and that of neutron is 0.028 electron volt, and electron in the range of 150 electron volts commonly. So interact with the electron, penetrating is much higher in case of neutron, because it's a neutral charge, in penetration is much high, interact with the nuclei. But in case of X-ray, it interact with electron and it's penetrating, but it's less than that of neutron. But if you see the electron, they interact with the electron and less penetrating. So among these three, only neutrons are interact the nucleus, whereas X-rays and electron, they will interact with the electron. And then how this different in case of X-rays, you see the Compton effect, photoelectron effect, and the photoelectron effect is related to the X-ray photoelectron spectroscopy, how this neutron interaction related to the neutron diffraction and neutron scattering analysis, and electron interaction related to generate secondary electron and backscatter electron, that will be used for scanning electron microscope, or transmission electron will be used for PM transmission electron microscope, or you can generate this X-rays, or it can generate that quasi-electron will be used for quasi-electron spectroscopy, that we'll discuss. And this is the interaction nature, that you can see X-ray. All of this you can go the absorption and scattering both neutron and X-rays, and different phenomena it occurs. In case of neutron electron, we see how this phenomena occur. Mostly we will study this in next class. We'll X-ray diffraction characteristics. Okay, so if there is any doubts, you can raise questions. I think since there is no question, so we'll conclude here. So we'll meet on day after tomorrow for the next class.